Can everyone hear me okay? Is that all right? Good. Okay. Yeah. Thanks to Gato, and thanks also to the organizers who clearly felt they should leave the best to last. Sorry, bad English sense of humor. Okay, so yeah, I'm going to also be talking about testing aspects of gravity beyond gravitationally induced entanglement, but perhaps in a slightly different way to the last talk. Okay, so in order to motivate this, I'm first actually going to try and review a little bit gravitationally induced entanglement. Okay, so I'm going to start, as Flaminia said, with Feynman, who at the famous Chapel Hill conference in 1957 spoke about how you could place a macroscopic mass in a superposition of two locations, okay, these circles on the left, using a Stern-Gerlach experiment, but he doesn't explicitly say how you do this. It was mainly just a thought experiment. Okay, now I should say at this point that for those of you that are in Canada, okay, this is a much more serious talk than what I gave there. Okay, so I'm not going to be using the faces of Chiara Miletto and Zagato Bose for the pictures of the masses, okay, for comic effect. Okay, instead I'm going to use Carlo and Marius, okay, particularly so Carlo gets to feel what it's like to be in a superposition. And in this case, if gravity is quantum, right, then we should think that the gravitational field should also go into a superposition with the mass, with Carlo. And then the mass on the right, should see this superposition and then would go into a superposition branch with Carlo of either going in the direction of upward Carlo or downward Carlo. Okay, so Feynman doesn't say this in the Chapel Hill conference, but what's happening is that the full system is becoming entangled. Okay, if we have Carlo up, okay, then Marius goes up with him. Okay, whereas, well, in a superposition, there's also Carlo down and Marius going down with him. Okay, so it's entangled. But if we have a classical theory of gravity, okay, then I'm going back to just the masses now. Then we cannot have a superposition of gravitational fields by definition. Okay, so this mass on the right will not see a superposition, so it can't go into a superposition branch with this left mass. Okay, so the state is a product state of the masses. For example, if we had semi-classical gravity, okay, where the gravitational field is sourced by the expectation of the stress energy tensor for matter, then we'd expect this right mass to just feel a force to the center of these superposed states. Okay, so quite remarkably, I think, with this quite simple sounding experiment, we can see effects of a quantum theory of gravity in the lab. Okay, and that was, further emphasized by Marius and Carlo a few years ago when they showed that if you think about this in a relativistic context, then we can think of this left mass as placing space-time geometry into a superposition, and then the right mass will see space-time curvature in a superposition, and the whole thing will become entangled. So I think a really beautiful picture of the experiment and driving home the fact that we are seeing quantum gravity in the lab. So now with the advent of quantum technology, there's much effort in many institutes around the world trying to make this sort of experiments a reality, and of course, very much here in Vienna as well. But arguably, you could say that a version of this experiment was actually performed over 40 years ago and before quantum technology. Okay, and this is the famous Page-Garker experiment, okay, which is kind of like Feynman's, but now we have a sort of Cavendish-like setup where this probe mass that was Marius, the one on the right, is now replaced by two small masses at the end of a torsion balance, okay, that we can see from above and from the side here. And rather importantly, we have to assume, we assume that there's the many worlds interpretation of quantum mechanics. Okay. Also, we have to put another famous experiment into the mix, okay, because there's radioactive material in this experiment. And rather than putting a cat into a superposition of dead or alive, instead, it is meant to place the experimentalist. So let's say it was Don Page. So this same Don page that we heard about in the very first lecture, okay, on page curves. Okay, so this is meant to place him into a superposition of placing some source masses in position A with respect to the torsion balance, and a superposition branch in position B. Okay, so it's a bit more complicated than this, but it's kind of like if there was radioactive decay, then he would place them in position A, and if not, he would place them in position B. So then if we have Everettian quantum gravity, which we heard on the second day was of much interest in the 70s and 80s, okay, then what we have is a globally entangled state, essentially, although it is a bit more complicated than this. But there was a branch where Page places them in A, and then the torsion balance responds to this, responds to the gravitational field, okay, and rotates clockwise. And a branch where it goes anti-clockwise. Okay. So then when Page looks at the torsion balance, okay, he should see a direct or an exact correlation between where the masses have been placed and the rotation of the balance, okay, because it's entangled. If, on the other hand, gravity is classical, then, as we said, there can't be in a superposition of gravitational fields. Okay, so then he wouldn't see exact correlation between the position of the masses and the torsion balance. Okay, for example, in semi-classical gravity, if we were to take the expectation of the global wave function according to many worlds, okay, then you would not expect to see any rotation of the balance at all, okay, because it's like all the masses are there at the same time. We have the average, and so the forces cancel out, and so you don't see anything. Now, of course, they did see exact correlation in this experiment, so it rules out then a classical theory of gravity. Okay, so then what's all the fuss about in trying to make Feynman's experiment in the lab? Okay, well, as you can imagine, there's some major assumptions and loopholes that go into this experiment, although actually I think this was quite an ingenious experiment. Okay, so one is that we have to assume that Page is trustworthy. Okay, we have to assume that he did what we thought he was going to do in every branch. Okay, and of course we have no way of actually knowing that. Okay, he could have done something not expected at all. It's also testing a specific version of classical gravity. It's testing Everettian classical gravity. It could be that we have semi-classical gravity without the expectation taken over the global wave function, or we can have something entirely different, like a stochastic theory of classical gravity, like by Jonathan and Diossi, which are considered more consistent theories of classical gravity. Okay, so there is strong reasons to still try and do Feynman's experiment beyond this many worlds interpretation. Yeah, so far I've been speaking of entanglement as being this necessary signature to see effects of quantum gravity in this Feynman and Page-Gaoka experiment. But as far as I'm aware, this wasn't spoken about until much, much later. Okay, so possibly the first to suggest this along these sorts of lines was Catherine Taylor when they introduced, they proposed a Page-Gaoka experiments beyond this many worlds interpretation, so the observers are not in the superposition branches. And they later connected this with this idea of LOCC, local operations, and classical communication cannot create entanglement, as we heard in the last talk. Okay, but then a revolution really occurred, as I think we all know, when a remarkable paper by Segato and his collaborators came out, which I think was independent of Feynman's idea, but in a way kind of showed how you could make something like Feynman's experiment an actual physical reality. Okay, so here they think about masses with embedded spins and send them through Stern-Gerlach experiments, okay, so that you see how now you would get this macroscopic superposition. And they talk about how if you put the probe mass as well as the source in a superposition, then you can use much, much smaller masses now than what Feynman alluded to, which was the Planck mass. Okay, so getting much closer to realization. They also showed how, from relativity, you could then argue that classical gravity should act as something like an LOCC, and therefore entanglement is really the thing you should be looking for in this type of experiment. At the same time, of course, there was also a paper by Maletta and Vedral, okay, arguing for a similar type of experiment. But actually, they argued that entanglement is a more general signature of quantum gravity than LOCC, a bit more along the lines of what I discussed with Feynman's experiment. Okay, so that led to an explosion of interest in gravitationally-induced entanglements. It gave many more ideas and also how you could look for these effects in experiments. And one important example of that is one by Kristander and the collaborators, where they showed that you could also look for gravitationally-induced entanglements between two trapped macroscopic quantum oscillators, okay, which could be in squeezed or coherent states rather than distinct locations. Okay. All right, and now for something completely different. I was told I had to use this slide again. So that was my introduction to gravitationally-induced entanglement. Okay, sounds very exciting, very promising. So why then would we want to look beyond this? Okay, similar to the last talk. Okay, so one reason could be that, although certainly not impossible, okay, these experiments are still very challenging and likely some years away, although maybe Marcus can tell me more on this. So for example, with the Stern-Gerlach experiments, the masses that you require in that case are still 8 to 9 orders of magnitude greater than the masses, or the largest masses that were so far put in a superposition of distinct locations, which was here in Vienna. Amongst other things, also just measuring entanglement between two macroscopic masses is also just going to be a challenging measurement process in itself. As we heard in the last talk, also there were some theoretical questions on how reasonable is LOCC and how general is entanglement as a test of quantum gravity. Okay, so while advances in theory and experiments might help with solving some of these concerns, I think we can also explore alternatives to see if that can also help. Okay, and that I think was kind of perfectly illustrated by a paper that was published last year, okay, where they showed that, they pointed out that the set of non-LOCC channels is larger than the set of entangling channels. Okay, so if you think about that hints that there could be then, or we should expect there to be signatures of entanglement, signatures of quantum gravity beyond entanglement if we assume that classical gravity is LOCC. Okay, and they also illustrate how this could potentially lead to experimental improvements. So for example, if we take this Kristander setup of the oscillators, then in the Newtonian regime of the interaction, okay, which is, so this is the quantum Newtonian interaction given here, this can be expressed as well-known operations in quantum optics, so beam splitting and two-mode squeezing operations. But if the gravitational interaction is much weaker than the free evolution, which you might expect from with near-future experiments, then often in quantum optics you neglect the last two terms in the so-called rotating wave approximation, okay, because they oscillate much more rapidly than the beam splitting terms, which you can see in the interaction picture. In that case, though, if you start with simple coherent states for the oscillators, okay, you don't get entanglement from these beam splitting terms. Despite that, though, they show that if you continue with this experiment, so you continue just with the beam splitting terms, then at a particular time, you find that coherent states get swapped. Okay, and that means quantum gravity will then be a swap channel, which is a non-LOCC channel. Okay, so this is something you'd get beyond LOCC, and yet the thing is not entangled. Okay. Actually, though they make this far more general, okay, quite remarkably, they derive a set of LOCC inequalities that, if violated in an experiment, would mean that the interaction channel is the non-LOCC unitary channel of quantum gravity. Okay, so, and they also show how that you could potentially look for this violation in just this Kristander setup by performing just local measurements on the two oscillators rather than having to do something non-local as in entanglement. Okay, and they also give some numbers for this, which in this case would give like an order of magnitude improvement over the time you'd expect to see entanglement in experiment. And they also give a Cavendish-like experiment as well, like the Page-Gaoka ones. Okay, so then you can see how this could potentially lead to more general evidence than entanglement for quantum gravity, and also it could potentially lead to some enhancements. So illustrating, why you might want to look beyond gravitationally-induced entanglement. To be fair to entanglement, though, let's have a look at if there are any disadvantages or open questions with this kind of approach. Okay, so one might be that if we look at these numbers for which they said you get an enhancement, the trapping frequencies are very small here. Okay, so this would be quite shallow traps. So this could be potentially experimentally challenging, and perhaps it's a question on if near future experiments would actually favor higher trapping frequencies, which actually would then favor entanglement over this type of test. Also, it could be that you could still get entanglement despite taking the rotating wave approximation if you change the setup a little bit, if you put in squeeze states, or if you could oscillate at the distance between the traps. It's a little bit unclear to me, once you include decoherence, how well these LOCC inequalities work, though I don't have time to go into detail. Interestingly, it's been shown that semi-classical gravity can swap states, okay, but not create entanglement. So in some cases, it actually might be less general than entanglement. And also, of course, it's based on the same principle of entanglement, LOCC, okay, which we heard from the last talk. So any theoretical concerns on that, okay, also going to apply here. Okay, so we heard about this already in the last talk, so I'm not going to spend too much time on this, but basically, some of these concerns, well, one is that since the experiment's operating in the Newtonian regime, okay, some have said, well, Newtonian gravity is non-local, okay, so then doesn't that mean that LOCC is always violated irrespective of whether gravity is quantum or classical, because the interaction is always non-local, okay? Our argument here is that yes, they are operating in the low energy regime of gravity, and yes, using quantum Newtonian gravity is a good approximation for the size of the entanglement effect, but still, we know from other experiments that the gravity is really relativistic, okay? It's never that it actually becomes Newtonian, okay? So, indeed, locality seems like a good assumption for these experiments. And we derived, to illustrate this point, we derived the entanglement effect using relativistic quantum gravity, which we heard in the last talk, where you split the metric into a background and a perturbation that you quantize. And then you find that entanglement actually only occurs after a period of time, because the time it takes for information to propagate from one of the masses to the other, okay, through the gravitational field. Okay, so kind of illustrating the locality of gravity. Some have gone further and said, well, okay, gravity is relativistic, but we still don't know if it could be non-local in the LOCC sense. Okay, so this would be something like relativistic action at a distance theory, which would be enough to create entanglement. Okay, so something like a Feynman-Wheeler type of theory, where now we don't have the gravitational field at all, we just have a gravitational force again, but this time it's a relativistic force. Okay, so it takes time for the force to be felt from one object to the other. Okay, so personally, I think that's kind of a question, but even so, if we did have such a theory, in my opinion, this would still be actually a quantum theory of gravity, because although if we apply this to the experiment, there wouldn't be a field in the superposition anymore, there'd still be a gravitational force in the superposition, okay? So seeing entanglement then would still be evidence of quantum theory of gravity, because I don't think a classical gravity theory should be able to put the force in a superposition. Okay, but those were just a couple of things about LOCC. As we heard in the previous talk, there's more question marks on how applicable is LOCC to these experiments. Okay, and so although personally I think it's a good assumption of locality, it would be good if we could find a signature of quantum gravity that doesn't rely on this LOCC principle, as we heard before as well. Okay, so that was a bit of a motivation behind looking beyond entanglement that we did a few years ago. Okay, so here, rather than using some general argument that classical gravity acts as LOCC, instead we looked at the low energy regime of gravity, okay, again, where you split the metric into a background and a perturbation. And in this case, the interaction Hamiltonian density between matter and gravity is given here. And then we looked at, what differences might you expect with a quantum to a classical theory of gravity? Okay, so in quantum gravity, you would quantize the perturbation, quantize the gravitational field, okay, but you wouldn't expect to in classical gravity. And then if we assume that matter obeys quantum field theory, at least within the regime in the experiment, then you find that the energy and momentum tensor is always quadratic in the fields. So that means that if you look at the interaction Hamiltonian and quantum gravity, okay, then you get something that's trilinear in quantum operators, whereas classical gravity would be quadratic, as long as you assume some sort of simplistic Hamiltonian version for classical gravity. I'll come back to that later. Okay, so then using tools of quantum information theory again, you can show that a quadratic Hamiltonian always preserves Gaussianity. Okay, so that means for a pure state, a state that's always fully defined by first and second moments. Okay, and whereas other Hamiltonians in general will induce non-Gaussianity, such as this simple Hamiltonian, which you might expect between matter and gravity. Okay, so then looking or seeing non-Gaussianity through a gravitationally interacting system, okay, could be a sign of quantum gravity. Okay, so then we applied this to a simple experiment where you have a single gaseous Bose-Einstein condensate, okay, self-interacting through gravity. And we showed that if you start it off with a squeezed Gaussian state, then after a short period of time, it will go non-Gaussian if gravity is quantum. Okay, and we found similar sorts of parameters as to the entanglement test, maybe slightly smaller on the mass, but not much difference. And just to say that first steps on this have been taking place in Nottingham, which will have some small results soon, but very, very small steps. Okay, so some advantages over entanglement then could be that you can apply this to a single system, you don't need two BCs, it just needs local measurements, as in the LOCC and C inequality tests. You can also rule out some non-local theories of classical gravity, such as those based on explicit non-locality in the Hamiltonian, okay, because although these are non-local, creating entanglement, they're still quadratic, okay, so they won't create non-Gaussianity. Some disadvantages though, so I said that this was based on the idea that matter obeys quantum field, which we know it does, but still, experiments don't often treat matter in that way, like microsolid experiments, okay, that's why we looked at BC instead. Whereas entanglement is more general, okay, so recently we showed how you can look for gravitationally-induced entanglement between two atom interferometers, which is based on the field picture. Also, although I said it can be more general in certain cases, in these non-local cases, likely it's not so general in others, just as with this LOCC inequality idea. So for example, it seems to work with semi-classical gravity and DOC-Penrose theory, whether it's local or non-local. But still more work needs to be done if it could work with Jonathan's great post-quantum theory of gravity or some Tilley DOC models. Kind of suspicious it wouldn't work so well. Whereas we know that entanglement will work as long as these like DOC-Tilley models will work if they're local. Okay, so there's three ways so far of looking at quantum gravity, evidence in quantum gravity, entanglement, LOCC, quantum non-Gaussianity. And what these all seem to be telling us, or what they all have in common at least, is that we have to look for quantum information properties, okay, to evidence quantum gravity. Okay, but that's always going to be challenging for these large objects. So it'd be great if instead we could look for classical-like quantities, okay, that could be easier to measure for these sorts of objects. But it doesn't sound terribly realistic because what we're trying to do is evidence the quantumness of some system. So therefore, it makes sense that we need to look for quantum information properties. Okay. Or does it? Because a couple of months ago, we showed that if you just start with the thermal equilibrium state of a BC, okay, and let it self-interact through gravity, then by just performing simple measurements of its heat capacity, you can also evidence quantum gravity. Okay, so the reason I think this works is because the natural state of a BC is actually a superposition of particles in and out of the condensate. Okay, and so if you have quantum gravity, okay, this then leads to a quantum superposition of gravitational potential energies. Okay, because the density profile of the condensate and non-condensate are different. This then affects the energy spectrum of the BC and then changes the heat capacity. Okay. But if you have classical gravity, as we said before, you can't have superposition, so there's the gravitational potential energy is always the same, irrespective of the superposition branch. Okay, so that then modifies the energy spectrum in a different way and leading to a different change to the heat capacity. And in fact, for semi-classical gravity with a uniform BEC, okay, we found that actually, interestingly, you just get a uniform shift to all the energy levels so that the heat capacity stays the same as if there was no gravity. So a clear signature between quantum gravity and classical gravity. Okay, so simple thermodynamic measurement for a thermodynamic object. So it sounds quite simple, but of course it also comes with some disadvantages. Okay, so one is that so far we've only compared the size of the effect to semi-classical gravity and quantum gravity. It'd be much better if we looked at something like Jonathan's model, which is more consistent. And it's unclear how general this can be made because it depends really on the size of the effect. And for the case that we looked at, in order to make this size of the effect big enough to be measurable, as with the other signatures, you really need to push the state of the art quite a lot. Okay, in this case, you really need quite demanding numbers on atoms and temperature. Okay, it's probably pointing to a new way to do a BEC, okay, which there are some ideas in the literature. Or maybe it's pointing to a different sort of condensed system, so something like superfluid helium, okay, which has more atoms in a particular experiment, so it might be better suited to that sort of case, and that's what we're looking at the moment. Okay, so maybe it didn't feel like it, but that was supposed to be a kind of short introduction into looking beyond gravitationally-induced entanglement. Okay, so there are many, many more ideas out there, okay, and more coming out all the time on this, okay, which I just do not have time to go through in 30 minutes. So, for example, Sakato's fantastic idea on measuring or testing the measurement postulates of quantum gravity, which I think is a really fantastic idea. Looking at violations of Legard-Gard inequalities, looking at quantum coherence, and more coming out all the time, and more ideas if you look in the poster session as well. Also, rather than looking for tests, looking for effects of quantum gravity in the lab, there are also ideas in looking for effects that you would associate with classical gravity. Okay, actually, so something like what Jonathan recently suggested, that you could look at a trade-off between decoherence and diffusion in general classical gravity theories, which would, might be much closer to realization than looking at quantum gravity effects. As with these other tests that I've looked at, you can always find advantages over a gravitationally-induced entanglement, but they also come with disadvantages. And so far, I'd say that there's not one clear approach that's much closer to realization than another one. But that's obviously what the hope is by continuing in this field, that we'll find a breakthrough and something that's much closer to experiments. I would say, though, that I don't think there's anything quite as conceptually beautiful as gravitationally-induced entanglement, and I don't think we'd ever get that. Despite that, though, I do hope that I convince you that this is an area that's worth exploring further, and something that I'm really quite excited by at the moment is not only can we look beyond entanglement, but can we also look beyond the laboratory? Okay, so can we take what we've learned about developing robust signatures of quantum gravity, okay, using quantum information theory for the lab, and can we now apply these to the cosmological and astrophysical settings, which are other places where we expect to see quantum gravity, as we heard on the first day. And I really think that has the possibility of opening up new ways of testing quantum gravity that could be closer to realization, or offering new aspects of gravity that we can't see in the lab. And also there's reasons to believe that these are places where entanglement could be challenging, like entanglement between two LIGO detectors, whereas these other alternatives might be more feasible, like non-Gaussianity in a single detector, or looking at LOCC between detectors. Again, I think that's worth exploring further, and hopefully would send us on a new path that could be closer to experiments. Okay, so that's probably really, though, for another talk, and maybe also another grant. And what I'll do is leave it there, not just say, though, thank you for your attention, but also thank you to everyone behind and involved in QISS. It's been an incredible 6 years, and I'm looking forward to it continuing in some form in the future.